Hello everyone. In this video I'm going to talk about the inverse Laplace transform, and from the title you have an idea of what's going to happen because you've done inverse functions, and this is kind of similar concept, even though it's not about the inverse function. So to show you what we're doing is, and there is a purpose for doing that, is we've done in the past creating this Laplace transform, let's say for function f of t, and having this capital F of s, or mapping on s, this other variable. And we developed some of them, and others we just say let's look at the table because they're kind of well established. So for example, when we use the definition of Laplace transform to come up with this transform for, let's say, a constant function, let's say 1, then we found it's 1 over s, with s being positive. So if it's 8, then 8 times 1 over s, right? And for this exponential function, we found that it was 1 over s minus a, right? And here I think I need to do s greater than a, not 0 here. Let's make this clear. Which is the domain, right? S greater than a. And for a power function, so now why I review this and talk about it, because I want you to keep attention to if you suspect a form, right, to look like n factorial, and if you see you have s power, let's say 4, then you may say, okay, then n could be 3, because if you have s power 4, then it is 3 plus 1. So you'll ask, do I have 3 factorial, which means do I have 3 factorial on top? So that's kind of the idea. And I'll talk more about others, but I think you're familiar with these. So what we will do with inverse Laplace transform is go now this way. You will have, let's say, 1 over s, and you'll find the function, the original function that was transformed. So we will go again from that domain of s to that working on the domain of t. Okay. And let's show you more. So if I have s minus a, you see now it's not s power n, it's s minus a to some power, let's say that 4, then I would suspect it's 3 plus 1, and I would look for or make up for the 3 factorial on top. These are also important. So if I have a quadratic form in the denominator, then I need to bring it to this given format so I can understand what A is and what B is. And if I do that, then I will look at the top. If I have B, then the original form is this, with sine of bt, the exponential function times sine of bt. But if I have s minus a, once I figure out this using complete the square, then I will kind of return to this, but it's going to be cosine of bt. So I think this gives you an overview of what's happening. And now let's go into some examples. We'll talk about this a little more, and then we do some examples on it. So as you see, since you have a table, you also have most of the work done. You just need to do some some of them will need a little more technical work or prep work than others to figure out what we have and what we need to come up with. So Laplace transform, of course, we looked at it as an integral operator, and it maps, as I mentioned, f of t into a function f of capital F of s, or a function on s, and it is an inverse mapping. So let's look at this example to understand the purpose as well. So let's say you have this equation, and you also have two initial conditions, and if we take the transform of both sides, so if you haven't done this in the past, you add both sides, subtract both sides, take natural log to both sides, you see. So now we're expanding that to, if we take the transform to both sides, and we use linearity, of course, because we saw that's one of the strong properties, is being able to use linearity here. Then we can get this kind of form, and here we know that this is Laplace transform of y, which is on t, right? And that's gonna give us some function which we called capital F. Let's call it here capital Y of s, or on s here, right? So, but this we don't know what this is, so let's leave it as it is. And we do know from the table for a t what that is, right? Because t is power 1, so it's going to be power of 1 factorial, and t to power 1 plus 1, which is square, but with s, so we're moving to s, right? All right, so we know the initial conditions, so we can use what we know to find, and also we know from previous section what is for the second derivative. So I'll write it for you based on what we did for this thing in the previous section when it came to properties of Laplace transform. We did for the second derivative. So let's write it here. We know that, for example, Laplace transform for a second derivative from previous section on s is going to be s squared Laplace transform of f on s minus s of f of 0 minus f prime of 0. So that's why we're given these as IVP, or as and these are provided, okay, initial conditions. Okay, so now we can use that for this here, which will give us s squared times some, you see Laplace transform of f is just some capital F on s, right? Then minus s f of 0, so s here we have y of 0, and minus f prime of 0, which is y prime of 0, which looking at this, it's going to be s squared capital Y on s minus, or of s minus 1. So now let's put back this into the equation. So now put this into the equation. We get s squared times capital Y of s minus 1 minus the capital Y already that we have there, minus 1 over s squared. Alright, so what's going on here? We have everything actually solved, and we know what the capital Y of s is. We just need to use algebra to get it done. And so go ahead and solve for y, capital Y here, and you get this, and multiply up and down by s squared to simplify this, and you get this way, and we can simplify a little more and get 1 over s squared. And then you'll say, you'll ask the question, which function f of t leads to that, right? And when you look at the table, or based on, if you recall it, it's just t, and on that. So what happens now is we figure out the solution, which means we figure out that this is one of the solutions for this problem is f of t, which means here, let's do a checkbox here. Maybe we'll do a different color. So does it work? That means if I do second derivative of t minus t equal, is going to be equal to negative t. Second derivative, the first one is 1, the second would be 0. You see, that works. And of course, if you use the initial conditions, of 0 is going to be 0, and of 1 is going to be 1. So when you put 0 for t, y of 0 is just going to be 0, and when you do first derivative, t prime is going to be 1, or y prime is going to be 1. So that also works. So this is a solution, and we use Laplace transform through the inverse of this transform to find the solution of the differential equation. And that's a powerful thing. This doesn't mean that the only solution is that, but we did find a solution. Okay, so here, based on this, we can say, we can give a definition. We can say that if you have f of s, the capital F, and if there is a function, and if there is a function f of t, or there exists a function, let's just say that if there is a function that is continuous on 0 to infinity and satisfies this Laplace transform of f is the capital F, then we say that there is an inverse. Then we say there is an inverse Laplace transform of capital F of s, which is what we just did. Okay, so let's do some examples. Let's say what is the inverse Laplace transform of 2 over s cubed? As I mentioned, now when you look at the table, you see s cubed, and you wonder whether there is some factorial on top. What the factorial should be is n plus 1, which is 2 plus 1, so you're looking at 2 factorial there, right? If it's there. What's 2 factorial is 2, so yeah, so that gives us that this is easy. We went back to t, so it's t squared. Alright, let's do more. Alright, let's say you have 3 over s squared plus 9, and of course this is to find the inverse Laplace transform, and that's s squared plus 3 squared there. That means this I only have a number, so it's 3, so it's that b there, which is sine of bt, which is sine of 3t. Alright, here is an interesting one that you need time to time is the top will decide whether sine or cosine, but the denominator here is something you will need to do often. Looking at this, remember it's a quadratic form, but it's not the form we used to, so we're going to do something that's called, and you've done in the past, complete the square. So you're gonna do s squared minus 2s, and here is plus 5. We'll take this divided by 2, square it, and add it here. That's 1. Because we added 1, we altered this quantity, and we're going to need to remove 1, so it's fixed. And now this is a complete square, which is s minus 1 times s minus 1, which is s minus 1 squared, right? And here it's a 4. Alright, so that gives us, and the top is just s minus 1. So we changed this standard form to something that involved a square, so we can see what it is. And the 4 also, we can change it back to 2 square. So this is a 4, which is a 2 square. And that gives us now what, because we have s minus t, when you look into the table, you know that this has to do with the cosine. So cosine of b, which is a 2, and now you're going to ask for a is 1, s minus a, s minus 1, so it's 1. All right. So these are 3 nice examples that involve what most of times you be dealing with. Let's give you now some properties with the inverse. Here is a theorem, and of course if you assume that you have inverse transform of f and f1 and f2 or f sub 1, f sub 2, and are continuous on some interval 0 to infinity, and c is a constant, so what you're going to be interested in is, does linearity work here? Which is yes. And that's a strong, powerful thing again to have. Linearity works on the inverse as well. Does a multiple work as well? Yeah. Which makes them easy to deal with. Alright, now let's do example. Let's do a big example. For example, let's see. Let's see. Let's say we have this and we want to figure out what is the original function here. So based on linearity and the multiple, we can do this. So this is, we've done stuff like this before. It just we do now in this context of the inverse. We have a common factor here is a 2. So let's take that out as well. Alright, so this we know uh, that it comes from the exponential function 6t, and this we know it's a 3 squared, so that comes from cosine. We have s here, not 3, so it's a cosine 3t. Alright, now what's going on with this? To know what it is, we have to use complete the square again. That's why I did that previous example. So 4 divided by 2 square will give us plus 4, which means you will have s plus 2 times s plus 2. Then you have 5. Then you subtract the 4 you're going to add. So that gives you a 1, which is 1 square. Alright, and here you have a number. That means you're dealing with sine. So here, because s minus negative 2, so a is negative 2, and sine, and that's 1t, which is t. Okay, so we have the answer here. Do more. Yeah, let's do 2 more. Let's, so you see the different techniques that are involved. Here is a simple one, but use something in integration like this. So here, when you look at this, as I mentioned, now you look at 4, then you say that must be some power there. So it must be 3 plus 1. But if it's 3 plus 1, I need 3 factorial there. I don't have it, I have a 5. Well, yeah, so I just put it there like you did in integration, and you need to divide by it, so you get rid of it. and now a 5 can come outside, and you have 3 plus 1 there. So now this is perfect. It's we know n is 3, and we know so it's 3 factorial, and that gives us for the answer is 5 6 e to negative 2 from here, and t cubed. Let's do one maybe involves some fraction decomposition stuff that you've done in the past. Let's say you have something like this. We already know that this denominator is going to give us some, complete the square, so 2 divided by 2 is 1 squared, so s plus 1 squared. Then you have a 10 minus that 1 would be 9, which is 3 squared. Alright, so then we have 3s plus 2 at the numerator. So we're going to, looking at this, we suspect that it's either we're going to deal with exponential at times cosine bt or times sine bt, right? So something like that. Okay, so I think we can go ahead and so it looks like a could be negative 1 and b 3, s plus 1, yeah, because we have this. So kind of, so looking back at the table, maybe I'll show you that. If you have this, of t here, of course, if you need to put, you put t there. So and of course you know the second one, which is that. And that's sine bt. So a is negative 1 and b is 3. So that's what we know so far, which means looking at these two and looking at what we have, it's hard to figure it out because you have 3s plus 2. But we can do the what we learned in the past with partial fraction decomposition, that if you have something like this, it could come from both. So let's just kind of set them up that way, then we'll investigate what happens. So we will say s minus negative 1, s plus 1, and it is. And the next one is with just 3 if you use b, right? Alright, and what you did in the past, you use so some A and B, and we need to determine those coefficients. Uh, so it's not bad, but once you know how to set it up, this setup is going to be the same all the time here. So 3s plus 2 is going to be a times s plus 1, so here, and b times 3 there. So it's going to be at the end, when you do that, you get as plus a plus 3b, which gives us that a from matching the coefficients there, determining the coefficients, equals to this. Alright, which gives us b to be equal to negative 1/3. Maybe I'll do that in here, because we can just solve it there. Alright, so that finishes this thing. So now what we have is what we're looking for. Yeah, negative 1/3 there. And now looking at the table, right, we know where this came from. So alright, so this gives us an idea that we can go into partial fraction decomposition and to do more, even though this one is just more of not really that much of that. It's just that we know based on the table, so I'll go back to that. So this is just from the table knowledge that if you have this, you're running into that or that, but we have this 3s plus 2, so we'll say maybe let's set it up based on uh, the 2 and put some coefficients there and see if we can come up with the coefficients, but they end up being easy to find and come up with the solution. If we need to do more, I'll probably do separate videos for the ones that involve the method of partial fraction decomposition, which is even the big one. Okay, thank you.